Hi, everybody. All right, chapter 4 and 28. So we get a little bit of a break from stoichiometry and doing the conversions and talk a little bit about the theory. So in chapter 4, a lot of this is kind of a review of what you had in middle school, but who knows? And there are some new things. Although the idea of waves and wave mechanics are not new to you, I think some of the calculations will be, but I don't consider this to be a particularly hard chapter. So um, really it's a this is this and that is that type of chapter, not really a process oriented chapter. So they start with, hey, what is an atom? And atom is fundamental building block of nature. It is not the smallest particle in the universe, but it is the smallest thing that has its own identity. So again, there are different types of atoms. There are gold atoms and silver atoms and copper atoms, but when you smack them open and the hadrons and leptons and all those particles come flying out of it, you can't tell one quark from another. They're all, you can't tell a quark that came from a copper atom because it's no different than a quark that came from a silver atom. So they no longer have their own individual identities. So the smallest particle that has its own identity is the atom. So there are different types of atoms. Now, our understanding of the atom did not develop overnight. There were some great scientists, and this chapter only mentions a few of them. There are some really good scientists that were left off the list. There'll be some more scientists that we discuss in chapters 5 and 6. But we're going to focus here on our understanding of the atom. How did it come about? So we're going to talk about a few different scientists here. And I'm going to start with Democritus. So again, feel free to take and pause these videos and take your notes and then come back to what I have to say. But with these scientists on multiple choice questions, and they do this at the AP level also, they're interested in, hey, what did the scientists contribute? And two, if there was a particular experiment associated with that, they want you to know what the experiment was. You don't have to understand, however, how the experiment worked, which I think is kind of silly. But in any event, Democritus. So in ancient times, people were philosophizing, trying to figure out what is the nature of matter, and there were two opposing viewpoints. One by a philosopher by the name of Democritus. And Democritus said that the world is composed of a fundamental material called an atmos, and that if you didn't have an atmos, everything else was just empty space. Now, this was a big deal philosophically. One of the most difficult concepts for people to think about is the idea of nothingness, this idea of empty space. What is nothingness like? It's hard to conceive nothingness. But eventually, Democritus said, if you broke things down, you would get to these little particles that were fundamental to making up all matter, and that in between these particles, there was empty space. But that wasn't an idea that caught on very readily. One, couldn't prove that the atom existed, and two, it was difficult for people to conceptualize what empty space was. The popular view was by a scientist named Aristotle. Now, I'm going to make this sound silly, but Aristotle is one of the greatest minds of all times. But this one he had wrong. What he said was that the world was composed of continuous matter, what he called Heil, and that different things had different types of matter that were unique to those things. For instance, a cat is made out of cat. A dog is made out of dog. There's some fundamental material that makes dogs dogs. And yes, you can break that material up. But once you start breaking that material up, the thing can no longer behave like a dog. The thing can no longer behave like a cat. So you are made out of you, Heil. I am made out of me, Heil. And that is actually a theory that was popular for a long time because it made sense to people that there was this nature to matter that made things what they were. In the late 1700s, a scientist by the name of Antoine Lavoisier comes around, and he's one of the first scientists. Him and Joseph Proust in Germany, pretty much at the same time, are both doing experiments with closed systems and writing down their discoveries from those experiments. So the idea of a closed system is we're not going to let any more material in. We're not going to let any of the material out. We're just going to see what happens when we change that material. And this led Antoine Lavoisier to the concept of the law of conservation of mass, which is very important because the law of conservation of mass shows us that the material doesn't just disappear. It can't be conjured up. It can only change from one form to another form. At the same time, a scientist by the name of Proust in Germany is working on his experiments, and this leads him to the law of constant composition. What he noticed was percent by mass, that water, for instance, was always 12% hydrogen, 88% oxygen. Didn't matter where he got the water sample from. Again, that shows this idea that atoms can move from place to place, but they're not created and they're not destroyed. Dalton. We always say Dalton is the father of the modern atomic theory, but there's very little that Dalton actually added to the theory. He was very good at taking other people's work and combining it for his own. He did come up with some things. So, again, there was a genius in putting this all together and discovering the patterns. But Dalton came up with these three postulates. He said that matter is composed of indivisible, not invisible. We know we can't see an individual atom because it's so small, but we can't see it because we can't detect it. Not because it's invisible. It's indivisible, which means you can't break it down any further. 2, atoms of the same type are the same, so gold atoms are all the same as each other. And different types of atoms are different from each other. Gold is different than silver. And that atoms combine together in whole number units to create compounds. Now, not all of this is correct. First of all, number 1 is not quite correct. We can break apart atoms, and their little atomic guts come flying out, protons, neutrons, etc. But again, they don't have individual character to them. They don't have individual, they don't have a unique attribute. In other words, again, protons from a gold atom look exactly the same as a proton from a silver atom, so they don't have their own identity. 2, atoms of the same type are identical to each other. That's not true either. Later they found out that there were isotopes. There's actually 3 different hydrogen atoms, and we're going to discuss that soon. Atoms of different types are different from each other. Yes, that is true. Gold is different than silver, and atoms combine in whole numbers to create compounds. Yeah, that was that whole constant composition thing. As it turns out, in order to have the same ratio of mass, you have to have the same number of atoms. So H2O is always H2O. Now remember I said that you want to know the scientist and you want to know what the scientist came up with. So they expect you to know these 3 postulates. J.J. Thomson in the late 1800s uses what's called a cathode ray tube, which is a tube that allows particles to move from one end of it to another. They used to make televisions out of them in the old days and computer screens, but that technology has faded into history. But anyway, he used these vacuum tubes to show that certain particles were attracted to certain surfaces. For instance, the existence of electrons. If he had a positively charged particle, and they knew about charges then he would shoot a beam of these particles and they would be attracted to a negative surface. So he said that the materials on the negative surface must be something called electrons. So he's credited with the discovery of electrons. And Millikan, an American scientist, he used what was called the oil drop experiment to calculate the charge on an electron. Now the charge is 1 times 10 to the minus 19 coulombs. So 0.00000000000000000000001 coulombs, whatever that means. So again, when they talk about charges, they use relative numbers. So if something has a charge of -1, it has half as much charge as something with a charge of -2. Again, they're all relative values. Rutherford's interesting. He was the head of the Royal Academy of Science in England in the 1920s, and he had the idea that, look, if there is an electron, like Thomson said, negative particle, well then it stands to reason that there should be a positively charged particle in the atom as well. And he designed what was later called the gold foil experiment. He said if you take small particles of metal crystals and small particles and bombard them at a sheet of metal, then we should see that these particles are either attracted or deflected. They should be attracted to electrons, and they should be deflected by or repelled by protons, what he called protons. So he took his two best scientists, Geiger and Marsden. Geiger later became wealthy. He developed what was called a Geiger counter, and that's used to detect radioactivity. Anyway, he takes his two most promising scientists and says, look, here's my idea. I'm going to have you guys run the experiment for me. Again, head of the Royal Academy. I guess he didn't have... well, you always have people working for you in that sort of business, so this would be typical of the time period. Now they kind of work in teams. It was a little different. But anyway, so Geiger and Marsden was like, hey, can we choose whatever metal foil we want? And Rutherford was like, go for it. So Geiger and Marsden was like, we choose gold. So it becomes known as the gold foil experiment. Now, they did have particles attracted. They had particles repelled. But they found that most of the particles went right through the gold foil. Some of them hit the gold foil and bounced straight back, but most of them went through it. And what they discovered through serendipity means by accident, was that the atom was mostly empty space, and that it had a small nucleus in the middle, apparently, where the positive particle was. So Rutherford, who designed the experiment, gets credit with the existence of protons and the existence of the nucleus, and Geiger and Marsden get credited for the idea that the atom is mostly empty space. There's an umlaut over that O, two dots that go over that O, and I believe it's pronounced Walter Berta, but I think if you call him Walter Both, he won't mind because he's dead. German scientist, 1930s, uses what's called X-ray diffraction. Now we're going to take a look at how particles disturb an electromagnetic field, and protons disturb it a certain way, electrons disturb it a certain different way, and there was a third particle that he found with a third disturbance pattern, and he called these neutrons because they had no charge, so the neutral charge. I always say X-ray diffraction is like looking at snow. You don't need to see an atom to prove that it exists. You can look at the X-ray diffraction and see what the atom did when it was there. It's sort of like a bear. If you look down in the snow and you see bear tracks, well, then you don't have to see the bear to know the bear once existed. You can look at the tracks that was left in the snow. And that's pretty much what we do with atoms. We take a look at how they disturb electromagnetic fields. This electromagnetic wave is called an X-ray, so it's just a certain type of field that we're looking at. Becquerel is a French scientist, and he is credited with discovering nuclear radiation. He did it by putting a slow-developing photographic plate in a drawer with a material he suspected was radioactive, and you could actually see the energy and particles flying out of the material and exposing the photographic plate. So he actually photographed radiation. And of course, Becquerel died from leukemia from being exposed to radiation. Okay, last scientist we're going to talk about, Albert Einstein. Now, Einstein wrote 3 pretty significant papers at the end of the 1910s, before 1920. And although he won his Nobel Prize for what's called the photoelectric effect, he is most famously known for E equals mc squared. He did not, however, win a Nobel Prize for this. It's called his theory of relativity. And what he was saying is, look, the smaller and faster you move, when you start moving close to the speed of light, you experience time and space differently than particles that move cosmically slow. So like the Earth moves at 25,000 miles an hour through space, but that's considered slow when you compare it to the speed of light. And electrons move at about 80% of the speed of light, so electrons do weird things. They disappear through walls, go somewhere and then come back. We have evidence of this. They bend around corners. Social distancing, good luck, because some of your electrons spread out from your body and actually touch other electrons from other people. Again, we have evidence that they do this. Now, how do they do it? Well, they have motion that we can't imagine. The smaller and faster you are, your behavior changes. Second thing he came up with is that mass and energy were related to each other. They were interconvertible. And one of the places where this occurs is in a star, where atoms fuse together, and in that process they release a tremendous amount of energy. So again, E equals mc squared, theory of relativity. Little things that move fast act weird. All right, so that's it with this video.